Alright, I'm going to do two more conservation problems. They're conservation problems that are going to use the vena contracta that I talked about in the last video. They're just going to use that effect. So let me just go ahead and pull up the first problem with the Venturi meter here. That's problem number 12. So if you look at the Venturi meter, what we're basically going to do is solve for the volumetric flow rate at the inlet in terms of all these symbols here. So the capital A is going to be the cross-sectional area at point 1 here, so from here to here, that's capital A. Lowercase a will be the cross-sectional area at the throat, here to here. G is gravitational constant. Delta H will be the height of the mercury fluid in the manometer. So we have a manometer that's flowing from point 1 to point 2 in the U shape like this. And rho is going to represent the density of the fluid inside the Venturi meter, which is isopentane. And then rho m is going to represent the density of mercury inside the manometer. That's the manometer fluid. And CD is the discharge coefficient. Alright, so this is my drawing that I made of that problem. So we're going to start off with the generalized Bernoulli expression again and start eliminating things. So there's no work, no pumps or turbines, no frictional effects, or the frictional effects are negligible over the short range, no potential energy, same elevation between point 1 and 2. Yeah, so that's all that we can cross out from our generalized Bernoulli expression. So next we are just going to want to define one of these velocity terms in terms of the other velocity terms using the continuity expression. So we know that Q is equal to U1 A1, which is equal to U2 lowercase a. And then we just solve. I'm going to solve for U2. So U2 will equal U1 capital A over lowercase a. So if I plug this expression into the generalized Bernoulli that we simplified over here, I have U1 squared over 2 times capital A squared over lowercase a squared minus 1 plus P2 minus P1 over rho is equal to 0. Alright, so now we just want to use the manometer and the height of this fluid to express one of these or both of these pressure terms in terms of some other variable. So I'm going to just call this point alpha right here, call this point beta, and this point gamma. So one thing to note is that this is mercury, and mercury has a very, very high density, especially when compared to isopentane. So we can say that rho m is much, much greater than rho. So what that allows us to do is just say that P1 is going to approximately equal our P alpha, and then our P2 is approximately equal to our P gamma. And that's looks like a rho, but it should be a P, so P alpha. Okay, and then from this hydrostatic equilibrium, we can see that our P alpha is going to equal P beta. So I'll say that P1 is equal to P beta, and then P beta will equal P gamma, which is approximately equal to P2, so it's going to equal to P2 plus rho m g delta H. Okay, so I can plug this expression that we just derived for pressure 1. So P1 equal to P2 plus rho m g delta H in. I can plug that into the generalized Bernoulli expression up here, and then you can see that the P2's will cancel, and then we'll have rho m g delta h over rho as a term. So I'll go ahead and do that over here. Okay, so next would be to solve for the flow rate. So we can do that. So we have U1. So I guess to solve for the flow rate, it'd be good to know that Q is going to equal to our discharge coefficient multiplied by the inlet velocity multiplied by the cross-sectional area of the inlet. And that's just taking advantage of the venta-contracta relationship. So now let's go ahead and solve for Q. So Q is going to equal CD A times U1. So we need to solve for U1. So U1 is going to equal, let's go 2 times rho m g delta h over rho, and that's a capital A squared over lowercase a squared minus 1 on the denominator there, and we're just going to take the square root of this whole quantity. So yeah, that's the algebraic expression of our volumetric flow rate coming in. And just looking at it, it looks like there's a problem with a negative sign somewhere in here. Yeah, it's right here. So right here, this should be negative, and then that would make this negative as well. So when I solved for this in my head, I subtracted this over, so this is still positive, multiplied it by 2, and then divided by this, which gives me this, and then I took the square root of that. So that would be the velocity. So this is the volumetric flow rate. So next up, we're going to look at a problem dealing with a tank of water draining with a sharp edge. So we're also going to have another venta contracta problem. So let me just go ahead and pull that up. Okay, so in this problem, problem number 15, we have two immiscible fluids in a tank. We have oil and water. And then we're given the cross-sectional area, which we're calling capital A of the tank. So it's capital A from here to here. And then we're draining through this orifice right here, and it's a sharp-edged orifice, so we are going to get the vena contracta effect, where the lateral momentum of the water draining following like a streamline like this will cause the contraction of the outlet stream, so that you'll have a narrower cross-sectional area right about here before the water starts flowing straight down perpendicular to the bottom surface here. So we're told to neglect friction. We're told that this lowercase a, which would be the lowercase a, is the cross-sectional area of the orifice exit, so not the vena contracta cross-sectional area. So right here is lowercase a. We're told that we can basically neglect the larger velocity, or sorry, the velocity associated with the larger cross-sectional area, just because that larger cross-sectional area is so much greater than the orifice exit. It's a closed system, so there's no inputs. That will be important later on. And then we're interested in deriving an expression for the time that it takes to drain all the water. So not the oil, just the water. So how long until h of t equals 0. So let's go ahead and get started on this problem. So first thing I want to do is just label some points on our picture here. Okay, so I'm going to call this right here a point, and I'm going to call this right here a point. So this will be my point 1, and this will be my point 2. So lowercase a is this orifice, and then the point that I'm looking at right here has a different cross-sectional area than the orifice. This is the vena contracta. So next what we want to do is just take a look at our generalized Bernoulli expression and just start simplifying. So there's no work, no friction. P1 is so P1 is equal to P ATM. If we were working in gauge, we can just cross that off, but I'll just keep it as it is for now. P2 is going to equal P atmospheric plus rho of the oil times gravitational constant times the capital H. So let's see here. We know that we can basically neglect U2 here, and we're neglecting U2 again just because A is so much greater than lowercase a. Alright, and then we just want to solve for velocity now. So let's just go ahead and rewrite everything that we have simplified. So u1 squared over 2 plus g, and then we're going from here to here, so our height is just approximately h of t. It's a little bit greater than that, but we'll just call it h of t. It's close enough. And then we're going to do P2 minus P1. So the atmospheric pressures will cancel out, and we'll just be left with a negative rho GH. See, no, it's going to be positive. So positive rho naught G capital H over rho W. And that will equal 0. So U1 is equal to 2 times 2G. You redo that. 2G times rho OH over rho W plus H of T. And then the square root of that. Okay, so that is the velocity coming out of at this point right here. And the next step is to just kind of look at this entire system and do a mass balance on it, because again we're interested in solving for time. So let's go ahead and just say that accumulation is equal to in minus out plus or minus source slash sink. And then we're just going to note that if we view this as our system, this entire box, then there is no input, so there's no in. And then there's also no source or sink. So we're just saying that accumulation is equal to the negative out. So accumulation is always a derivative term. So our derivative term is going to be, so change in mass, I'll just do it over here, dm dt is equal to a negative m out. That's basically what we're saying. Now, when we're interested in the mass of water, we can define the mass of water as the volume multiplied by the density of the water. So I can rewrite that expression as, and then I can also note that the density of the water is constant, so I can pull the density out in front. So I can say rho dV dt is equal to, then I can also say that the mass leaving, well, that's going to be equal to the flow rate multiplied by the density of the water. So the flow rate again is going to be equal to Q times, let's see, so let's look at a continuity expression. I'm going to do it up here. Sorry, I'll do it down here. So Q is equal to A1 U1, so A1 corresponding to this, which is equal to A2 U2. So we don't know A1, but we do know lowercase a, so we can say that A1 is actually equal to the contraction coefficient of contraction multiplied by U1. So and then we can plug that in up here, and we can say that Q is equal to CC multiplied by lowercase a. Sorry. Let me go back. So A1 is equal to CC lowercase a. So that Q is equal to CC lowercase a U1. So this is our Q, and we know that the mass leaving the system is going to equal to a negative rho multiplied by CC lowercase a U1. So the rows will cancel. And then if we're interested in the volume, so volume is going to be the diameter of our tank here multiplied by the height of our tank. So that's going to represent the volume. Or I suppose actually it's going to be the cross-sectional area, not the diameter. So it'll be, so we can pull the cross-sectional area is not changing, it's constant. So I can pull that out. So I can rewrite this as A times the d h of t dt, which is equal to negative cc lowercase a, and then I can plug this expression in. Yeah, I'll go ahead and do that now. So it would be times 2g rho of oil times capital H over the density of water plus h of t, and we'll take the square root of that. So now we need to separate and integrate. So let me just scroll down. Okay, so I'm going to multiply the dt over to this right hand side, and I'm going to divide this entire expression over on to this left hand side, and then I'm just going to pair things that I can pull out of the integral. So if I say that t is equal to negative a over the coefficient of contraction multiplied by the orifice cross-sectional area, and then this is going to be divided over here, so it's going to be a square root of 2g. I can pull that 2g out and just leave this inside the integral. So then I'm going to integrate that from 0 to h. So I'm just integrating over the initial height. So let me scroll up, I'll show you. So in the problem statement, we're told that initially the entire system was filled to this level, and then it started draining, and then after some time t, we're looking at a snapshot where h is no longer, this lowercase h is no longer equal to the initial value, but we're sometime later. So if I'm interested in the total time to drain from the initial volume to the end volume, then I'm going to be integrating from 0 to capital H. Okay, and then I'm going to be, let's see, so I'm dividing this expression over, so it's going to be dH on top divided by the square root of density of oil times the height of oil density of water on the bottom there, plus H of T. Alright, and then we can use an integrating table. So let me go ahead and look up that identity, and I'll be right back. Okay, so I found an identity that will work. So I'll write the identity right here. So we can say that the integral of dx on square root of a plus bx is equal to 2 on b times the square root of a plus bx. Okay, so let's go ahead and use that identity now. So A is going to be our rho O, H, rho W, B will be 1. And so that will give us T is equal to negative A over CC A square root of 2G. Then we'll have, let's see, I can pull a 2 out here. So 2. And then we have the square root of our rho O H on rho W. And then we'll be adding our H of T. And then the bounds of that are from 0 to H. So in a final step here, we can say negative 2A I'm going to multiply that by the quantity. Now if I plug H in here, I can get a square root. So we have rho O H rho W plus capital H, and then where you're going to subtract from that the square root here of rho O H and rho W, and then the 0 in for there. So that is the final answer there for this problem. So that is the time to drain all the water from the tank.